Welcome to this video on kinematics graphs. In physics, we often represent the motion of an object using three fundamental graphs: position versus time, velocity versus time, and acceleration versus time. These graphs help us visualize and understand how objects move. Let's start by understanding what each graph represents. We'll explore several different motion scenarios and see how they appear in each type of graph. Throughout this video, we'll analyze these four cases: constant velocity, constant acceleration, variable acceleration, and a special case, simple harmonic motion. Before we dive into specific cases, let's understand what these graphs mean. In a position-time graph, also called an XD graph, the vertical axis represents the position or displacement of an object, while the horizontal axis represents time. In a velocity-time graph, or VT graph, the vertical axis represents the velocity of the object, while the horizontal axis is time. Finally, in an acceleration time graph, or AT graph, the vertical axis shows the acceleration of the object, with time again on the horizontal axis. Now, let's examine our first case, motion with constant velocity. When an object moves with constant velocity, it means it maintains the same speed and direction throughout its journey. Let's see how this appears in our three types of graphs. In the position time graph, constant velocity appears as a straight line with a slope. The slope of this line equals the velocity. In the velocity time graph, constant velocity appears as a horizontal line, showing that velocity doesn't change with time. Finally, in the acceleration time graph, constant velocity results in a line at zero, since there is no acceleration when velocity is constant. Now, let's look at our second case, motion with constant acceleration. This is the case of an object speeding up or slowing down at a constant rate, like a car accelerating from rest or a falling object under the influence of gravity. Let's examine the graphs for constant acceleration, assuming the object starts from rest. In the position time graph, constant acceleration appears as a parabola. This is because position increases quadratically with time when acceleration is constant. In the velocity time graph, constant acceleration appears as a straight line with a slope. The slope of this line equals the acceleration value. And in the acceleration time graph, we see a horizontal line at a constant value, showing that acceleration doesn't change with time. Let's move to our third case, motion with variable acceleration. This occurs when the rate of change of velocity is itself changing, like a car that increases its acceleration over time or a rocket that has variable thrust. For this example, let's consider linearly increasing acceleration. In the position time graph, variable acceleration creates a complex curve that's more steep than a parabola. In the velocity time graph, variable acceleration appears as a curved line. In this case, a parabola, since acceleration is linearly increasing. And in the acceleration time graph, we see a line with a positive slope, indicating that acceleration is increasing with time. Finally, let's explore our fourth case, simple harmonic motion. This is a special type of oscillatory motion where the acceleration is proportional to displacement but in the opposite direction. Think of a mass on a spring or a pendulum. Let's look at the graphs for simple harmonic motion. In the position time graph, simple harmonic motion appears as a sine or cosine wave, showing the periodic oscillation of the object. In the velocity time graph, we also see a sine or cosine wave, but it's shifted by 1/4 of a cycle. When position is at its maximum, velocity is zero, and when position is zero, velocity is at its maximum. In the acceleration time graph, we again see a sine or cosine wave, but it's shifted by half a cycle from the position graph. This shows that acceleration is always directed toward the equilibrium position. Now that we've seen all four cases, let's compare all the graphs together and understand the important relationships between them. The key insight is that each graph is related to the others through calculus. The slope of the position time graph gives us velocity. The area under the velocity time graph gives us displacement. The slope of the velocity time graph gives us acceleration. The area under the acceleration time graph gives us the change in velocity. Let's visualize all our cases side by side. Here we can clearly see the characteristic shapes for each type of motion across all three types of graphs. For constant velocity, we have a straight line in the position graph, a horizontal line in the velocity graph, and zero acceleration. For constant acceleration, we have a parabola in the position graph, a straight line in the velocity graph, and a constant value in the acceleration graph. For variable acceleration, we have a complex curve in the position graph, a curved line in the velocity graph, and a linear change in the acceleration graph. For simple harmonic motion, we have sinusoidal waves in all graphs, but with phase shifts between them. To summarize what we've learned, 1. The position time graph shows us where an object is at any given time. 2. The velocity time graph shows us how fast an object is moving. 3. The acceleration time graph shows us how the velocity is changing. These 3 types of graphs are powerful tools for understanding the motion of objects, and the relationships between them help us analyze complex motion problems. Thank you for watching.